interdisciplinary water governance. And now I thank you very much again. And now I go forward for this, and I am going to invite our next speaker, Dr. Muhammad Tousif Bhatti from IMI Lahore, and his topic is the verification of rainfall forecast for developing an SMS advisory service. Before you start, Dr. Tosif, I will introduce you. Dr. Tousif Bhatti is an eminent researcher at International Water Management Institute, Lahore. He brings around 15 years of experience in multi-facets of water source engineering, irrigation, agriculture, water management, and hydrological system. But he has spent more than a decade working on research and development projects. He has filed many roles in his career, including trainer, educator, researcher, project manager, and consultant. Dr. Bhatti has strong interest in hydrometeorological instrumentation for automated data acquisition and decision support system development. Please, Dr. Bhatti, I am going to invite you for your special lecture. Please, Dr. Bhatti, you can present.
Thank you very much. And a good morning, good afternoon, and good evening based on the time zones you are listening to me. And I'm also on the road. So in the interest of bandwidth, if you allow, I can switch off my video and share my screen.
Okay, you can do.
Thank you. So please confirm when you see my screen
We
and
can
if
see
I'm
now. Yes,
audible.
we can see.
Okay, thank you very much. So my name is Tousif and I work for International Water Management Institute. And in today's special lecture, I will be presenting a recent research work we have done in one of our projects. Its title is Verification of Rainfall Forecast for Developing a Farmer's Advisory Service. So the flow of presentation will be like, first of all, I will give you a brief about the challenge we are trying to address in this research. And then I'll explain the sources of weather forecast. And then I'll let you know that how we have developed this farmers advisory service. It's an SMS-based service. And then a specific part of analysis that will deal with the verification of rainfall data for developing this farmer advisory service. And then I'll conclude my presentation. So I'll start with the challenge. We know that rainfall is one of the major source of irrigation in wide part of the globe, especially in the rain-fed irrigated areas. The farmers totally rely on the rainfall as a single source. But in irrigated agriculture areas, still rainfall is relevant and it plays a vital role in supplying the irrigation to the farms. But in developing countries, the farmers have very little knowledge of the weather forecast information sources, and they have limited access to the technology like the internet and smartphones to make use of these forecasts. And these forecasts can inform the farmers to make the expensive irrigation decisions, whether they should irrigate their field in the next week or say 2 weeks time, or should they abstain the irrigation based on that information. So this is the challenge, that how we can provide weather forecast information from the sophisticated models to the farmers in a timely and understandable manner. Um, this research work, I present a case of developing the farmers advisory service. I'll give you some features of this, and which is based on the forecast data, obviously. And I will also be presenting the analysis that emphasizes on the statistical verification of a 16-day rainfall forecast data, which we have obtained from the global weather forecast model, which is called the global forecast system. So a few words about the weather forecast data. There is a wealth of weather forecast data that is publicly available through various mobile applications. You must be using one of these applications on your mobile phone. You see the widget every day when are you planning a visit or travel. So few examples are the AccuWeather, dark sky, open weather, and blah blah blah. But from where these applications get the weather forecast or predictions? In fact, this information is coming from the very sophisticated numerical models, which are run um, by the supercomputers, you would say. And some of these examples are the global forecast system, which is one of the most sophisticated data set. Uh, and National Oceanic Atmospheric Administrative NOAA, which is a very famous government agency of the United States that maintains this global forecast system. And then there is global environmental multi-scale model, European Center model, weather forecast, United Kingdom Meteorological Office. They have their own models. And all these models are run at different geographic scales, and they get their input data from various satellite sources. So the output of these global models, like GFS, is publicly available, but it is acquisition of this data from their computers um, involves some sort of processing and automation and coding things. So are we reinventing the wheel in Pakistan? Because this sort of farm advisory service is very common in developed countries. Like in Australia, you would see some sort of advisory service which is provided on through mobile applications. Is there any service in Pakistan? The answer is yes, in public sector as well as in private sector. So in public sector, we have example of Pakistan Meteorological Department, which issues these bulletins, which include the weather forecasts, and also there is some text available for the farmers so that they can make an informed decision about the farming. But again, this data is coming from the same sources, like Pakistan Meteorological Department gets this weather forecast from GFS. Then in public sector, we have example of Pakistan Council of Research in Water Resources. This service is SMS based, and we have you can say that our farmer advisory service, the motivation to develop this farmer advisory service is based on this Pakistan Council of Research in Water Resources. But we have added some value in their service, and I would explain it in the coming slides. In private sector, you might have seen these applications. These are mobile applications, like Jazz is providing Bakhabar Kisan, and Telenor, it's Khushal Zimidar, and so on and so forth. So both public and private sector is providing in one way or other farm advisory services. But I will explain it how we have developed this farmer advisory service and what value we have added in a typical farmer advisory service. So in this flow chart, you would see that we have automated and coded all the data acquisition, data processing, data verification, and data dissemination, all four parts of the process. So in the first process, and you allow me, I can take the pointer. So the first part is the data management. We acquire observed weather data, we acquire weather forecast data, and agriculture data from the satellite and observed data. All data acquisition is automated. We don't sit on the computer and get this data from various sources. So everything is automated. That comes into SQL database, and from this SQL database, it is being verified. And for verification, we use different statistical models. I will explain a few models and matrices in the coming slides. And once we verify this data, we construct the message for our farmer advisory service. And that again involves some sort of automation and coding, and it involves translation as well. And finally comes the dissemination of our outputs to the farmers. That involves the SMS server and again some algorithms involved in that. So this is how we have developed our farmer advisory service. So what value we have added to the typical advisory services which are prevailing in Pakistan. So the first thing is that the forecast data is automatically acquired for the whole Pakistan, and it is archived in SQL database in a constructed way. And during this forecast data processing to construct the advisory service, we make a distinction between the irrigation and administrative boundaries. This is very important. I would emphasize that in your mobile phone or the advisory services, you would see the advisory for an administrative boundary, which is the city or tehsil of your area. But in our farmer advisory services, we are providing information based on the irrigation command area. So we draw a polygon for each of the irrigation system in Pakistan, and on the centroid, we collect the weather forecast data, and then we verify and then we disseminate it. At the moment, we are providing on a pilot basis for one irrigation system, but we acquire data for the whole of the country. So the Shamazai irrigation scheme, which is situated in Sawat area, we have rolled out this advisory service. Then another value addition is that that the communication channel, there could be many communication channels like radio, like mobile app, but as I have mentioned in my earlier slides, that farmers usually don't have access to internet and these communication channels. So we have made it very simple, and we have preferred the SMS, which can be sent out on an ordinary phone as a communication channel. And then we have taken care of translating the message into the local language. Currently, we are using the national language, Urdu. We are sending the information in Urdu language. So this is how we have added some value in our advisory service. Now I come to the second part of the presentation, which deals with the verification. So it answers the question that how confident we are about weather information sent out to farmers. Because it is very important, we should have confidence before sending this information, because the farmers who are the users of this advisory service um, would be using this information to make irrigation decisions that involve a lot of investment from the farmers. So we should be very sure about the information we are sending, that it is accurate to some extent. So in this verification process, we have procured the historic forecast data from GFS for about 1,000 days. The period starts on 7th of October 2017 up to 24th of June 2020. Just randomly, when we started this research, we picked this period of around 1,000 days. The data comes in rasterized form, from which we extract the time series for a point of interest. And this forecast is made every 6 hours, I mean, 4 times in a day. And each forecast has data for next 16 days in 3 hourly intervals. So for each forecast, there are 128 values, and it includes 17 variables of weather, including the rainfall. We have included only rainfall. We have picked only rainfall for the verification purposes at 15 locations. These 15 locations are, in fact, the meteorological observatories maintained by Pakistan Meteorological Department across the KP province. And in this slide, you would see the map, which is showing these 15 locations across the Khyber Pakhtunkhwa province of Pakistan. And these are the list of meteorological stations from which we have also collected the observed data for comparison and verification purposes. You can see that We have calculated the coefficient of variation for the annual precipitation for these 15 stations, and which is 54%. It shows that there is a vast variation in annual precipitation received at these stations. And also 63% variation in altitude shows that these observatories range from the very plain area in Di Khan to the mountainous areas of Kalam and Malam Jabba, which has the altitude of around more than 2,500 meters above mean sea level. And this is how a typical data set looks like. The important thing, you can see that for one stations, we get around 1 million records. And we have to process and extract this data from the rasterized data. This involves huge computation. Um, I will very quickly go through the types of verification and verification methods we have used. So first of all, you should know about what are the nature of forecasts. It could be deterministics, like the quantitative precipitation. It would rain around 15 millimeter per se. So this is an example of deterministic forecast. Probabilistic, you would get an idea that what is the probability of rainfall, 10%, 5%, and so on and so forth. So this is an example of probabilistic. Qualitative is the worded. You get the bulletins you see on the widget on your mobile phone. This is the qualitative forecast. But in our case, our data set is the deterministic or the non-probabilistic forecast. And it is in the form of time series. We have the daily rainfall forecast for a city, is an example, and it is continuous. It is not dichotomous. But the interesting thing is that we can convert the time series into a dichotomous or yes-no type forecast if we select a threshold. So we have converted our data set, which is in the form of time series, into dichotomous data as well by selecting a threshold. So then we apply these matrices. For dichotomous analysis, it is very typical. We use contingency table, which you can see here. For example, if the forecast say that it will rain and the observation is that it actually rain, then we call it as a hit. And if we forecasted that it won't rain and but it rain in reality, we call it a miss. And similarly, um, we see false alarm, correct negatives in this contingency table. And based on these hits, misses, false alarms, and correct negatives, we calculate different matrices. We have used 4 in our verification process, which are accuracy, probability of detection, false alarm ratio, and equitable threat score. What is important to know is what should be the ideal score for these matrices. So accuracy should have ideally 1, POD should be 1, false alarm 0, and ETS should be 1. And for our continuous variable analysis, we have used 2 matrices, which are the mean absolute error, which is very common error. It has the units of the same as whichever variable you are using. So in our case, it's millimeter per day. And we have also applied mean absolute scale error because in mean absolute error, you can't generalize it, or you cannot calculate the error across the stations. For that, we are using this scaled error, which get away from this problem of scaling. Um, it is, in simple words, it is a ratio of the error to the error of a naive method. Naive method means it is just based on unskillful or just historic data. We calculate a forecast, and it is in denominator, and as compared to the forecast which is skillful. So it ideally should be less than 1. So this is some more detail about these matrices we have used for dichotomous analysis. Accuracy answers overall what fraction of forecast we were correct, and our false alarm ratio, what fraction of predict yes events actually did not occur, and so on and so forth. So in these slides, these two slides, I will be presenting the results. Let me show you the legends for this. So first of all, for consistency, we are presenting uh, false alarm ratio as a complement. I mean, I have told you that accuracy, probability of detection, and equitable threat score should ideally have a score of 1. So ideal score is 1, but in case of false alarm ratio, the ideal score was 0. So we have used this complement FAR for consistency of this color scheme we have used. So now it is very easy to detect that these dark pink dots show very good um, results for these four matrices. Light pink are around 50% or zero point 0.5, and gray are undesirable, and black dots are really undesirable. So accuracy, you would see that most of for all the stations which are here in 15 rows, I've given the names in this small table, and on the columns you see the number from 0 to 16, which denote the forecast day. So you see that for all the stations, the accuracy was very good. But we see a very few pink dots for probability of detection, especially for 15, which is the Bala code. There are good results. There is one dot for Tir in day 1, but after that we get gray and black dots. So that means that probability of detection is not very good for across the stations. Similarly, for false alarm ratio, you would see that for station number 3, 7, 10, and 12, we spot some pink dots, but overall, it's not very good for remaining stations, and especially for the uh, the days starting from 8 to 16, we get not very good results. Equitable threat score, we don't get very good result here for this matrix. And these two graphs show the results for continuous variable analysis. But here
Okay,
you,
Dr. Tousif, we're a bit
yes,
short of time. Can you speed up and summarize yourself?
okay, okay, only a couple of more slides. So in this, the black and gray dots are showing the good results because the error is less when we denote it from with a black and gray dot. You would see that mean absolute error was small for some stations. So overall, there is a mixed result. I'll skip this slide because it's short of time, and I will conclude the analysis that the statistical indicator accuracy remained above around 0.8 85% of times over entire forecast time across all stations. In contrast, the statistical indicator probability of detection, false alarm ratio, and equitable threat score remained outside of a desirable range for most stations and forecast lead time. In the continuous variable analysis, we note that mean absolute scale error is quite high, particularly at the stations with high annual rainfall. And then we also conclude that the inference from mean absolute scale error of weekly average data shows that statistically it will be indifferent to issue the weekly advisory SMS on any day of the week. But in context of local practice, it would be more convenient for farmers to receive an advisory that coincide with the Barabandi week, that is through Saturday through the Sunday. So we are sending this advisory on weekly basis, and it should be sent on a particular day that our analysis suggests should be the Saturday. And false alarm uh, farmer advisory service has the potential for upscaling as most of the ICT and automation work has already been done. But how it influences farmers' irrigation decision is the subject of future research. For further reading, we have just published this paper. You can go through it. It's open access, and I'm open for questions. Thank you very much.
Thank you very much, Dr. Tousif, and we really thankful for this valuable informations.